reasoning?
Yes, I
Inductive.
have.
Okay. And the other one is called deductive
Yeah.
reasoning. So what is inductive reasoning? Like in your own words.
I might get them switched up, but I believe inductive reasoning is when, okay, so you walk, okay, so you put a slice of pizza in your fridge, you walk away, you walk back to your fridge and it's gone. Someone must have eaten it. That's inductive reasoning, right?
Well, that's actually not called inductive reasoning. That's it's more kind of detective work, right? You make sense of it. But you do use, when you're doing deductive work, you use both inductive reasoning and deductive reasoning. Now, inductive reasoning is what you do like physics, what you do chemistry, what you do social studies. It's basically you find some particular cases, and from that you make observation, and you came up with a general, with a generalization. Now, for example, let's suppose that you saw sunrise yesterday, and you saw sunrise the day before yesterday, and the day before yesterday, and then you can come up with a very reasonable conclusion that the sun will come up tomorrow, right? And you can even make that generalize into that the sun will rise every day. Good.
Yep.
So that's a general, when you generalize it, that's called inductive reasoning. So you're looking at things, you look at patterns, and you find some basically the basic rules. And that's what we do with science. Now, inductive reasoning, well, let's go back to deductive reasoning. Deductive reasoning is based on a general principle that then we came to particular cases. For example, this is actually really classic general kind of example of general inductive reasoning is that, first of all, we'll say all living human have to breathe. Okay, can we agree on that?
Do what?
All living human have to breathe.
Yep.
So this is very general, right? We're talking about all. We're not saying some, which is all. So all living humans have to breathe. So that we take for, take it for granted. We assume that it's true. Very, very general statement. Then we'll make that more, from the general, make that more specific. So we'll say that Dr. Ping is a living human. Can we agree on that?
Yep.
Okay,
Definitely.
and then, Definitely.
Definitely.
Okay. Then we can conclude that Dr. Ping has to breathe. Good?
Yep.
So this is called deductive reasoning. Now we came up with something very general, all living humans. Then we came down the conclusion that is Dr. Ping has to breathe. So that's called deductive reasoning. Now we talk about inductive reasoning is looking at the patterns. Then we came up with general rule. Now, deductive reasoning has the property that as long as the basic assumptions, they call basic principles, some call it first principles, are true, then as long as our logic is sound, then our conclusion is either true or false. Good? So that means we can prove something is true in this sense. But that's not true for inductive reasoning, because inductive reasoning, we cannot prove it is true. We can prove it is not true. Okay, do you see the difference?
Yes.
Now, for example, you look around in your room, you see it's flat, right?
Yep.
And you look at in your neighborhood, well, maybe you're looking in where I live, I say it's pretty much flat. Good.
Yep.
And you drive up to Chicago. I don't know if have you ever done that.
Yeah.
From yeah. So what do you see? Flat, right?
Yep.
The area where it's
Yeah.
flat. Now you can come up with a conclusion is that the Earth is flat.
Well,
Okay.
Yep.
Well, so far, based on what you see, that support that conclusion, right?
Yep.
Until what happens? Like until say if you get to the ocean and you
Yeah.
see the horizon. And now you see the horizon is not flat. Good.
Yep.
And then you move up, maybe you take an airplane, then you see that the Earth definitely is not flat. So even though there's some people still believe that, but we know most of us sensible enough to say, okay, we see it, it's not flat. So therefore, our conclusion is not true. Good.
Yep.
So that's what happens with all inductive reasoning is that we can assume something is true based on our observation. It's kind of like physics. We do experiments, we see something happens, we came up with we call it the law of the nature. And then until something else happens. Good.
Yep.
Now, for example, in the old time, not that old, we're talking about before the 1950s, all the scientists assume that we have no beginning and we have no end. That means that the time is infinite, no beginning, no end. And everybody has been kind of accepting it for pretty much thousands of, at least a couple thousand years, thinking that there is no beginning, there's no end. I mean, in terms of the physics, in terms of, the scientists. Of course, not in terms of theology. I mean, the Bible teaches us that we have a beginning, but as far as the scientists, before the 1950s, they pretty much holds the view that there's no beginning, there's no end. And then there's something happened. And someone came up with the theory of Big Bang. Now, Big Bang means basically we have beginning now, right?
Mhm.
And they actually did some experiment which confirmed that the Big Bang theory actually makes more sense. It doesn't say the Big Bang theory is true because we just cannot prove that. We can just assume it's true until something happens. So that is kind of nature of all the
Isn't
science.
Big Ben a clocker?
Huh? Big Bang is
Isn't Big Ben a clocker?
well, actually, the Big Bang is, I mean, if you're talking about the in the past 10 years, or maybe 20 years, a Big Bang, I think Big Bang Theory, that's a TV series. But the Big Bang Theory in physics, it just means that the natural world has a beginning. Everything started with a bang, with explosion, and why and how happened, we really just don't know. We just say it makes sense based on the mathematical model that there is the expansion of the universe, and that we actually can observe the universe is definitely expanding as far as we can see. But we just don't know if they will keep expanding or they come back or contracting. We don't know. We don't know if it's cyclical. So therefore, so for physics and all that, all the sciences except the math, they rely on inductive reasoning. Then all the theories is something we assume is true until it's proven not. So we can prove it's not true. Just like our flat Earth theory, until we go to the ocean, then all of a sudden we say, okay, it's not the case. And by the way, actually, more than 2,000 years ago, the ancient Greeks, they actually realized that the Earth is not flat. The Earth actually is round. It's kind of, to them, it's kind of like big sphere. They actually did a calculation about like how big Earth is, and fairly kind of accurate, given that It's more than 2,000 years ago. But anyway, that's the nature of the sciences except math. Math is different. Math is called deductive reasoning. We have this first principles we call axioms. And as long as our first, I mean, those basic principles are true, then everything we develop on top of that will be true. Okay, so that's why math, there's not much change as for so far. Like the geometry was invented, they invented more than 2,000 years ago. Pretty much all the theorems are still true. Almost all the mathematical theorems are true. It's because the nature of inductive reasoning. Good?
Yep.
And that's what's different from math to others. Math is called something called pure science. And everything else is called applied science. Good?
Yep.
So basically, we apply mathematics into the study of that. And so that's why sometimes the theories means a theory is a guide, but don't take it as if they are the same as the theories in math, which are different. Like especially the political science or social science, they are we just don't know if it's true until something happens which proves it is not. Good?
Yep.
Now, for example, this is a very, very, I don't know if you have learned that in the biology. And now, but you all heard about Darwin, right?
Heard of who?
Darwin,
Yeah.
evolution, Darwinian evolution.
Mm.
So,
Prob-
so basically, he believes that everything is evolved. As a human beings, we are evolved from basically the single cell, and
yeah.
and eventually, and his theory based on a gradual evolution. So things change slowly but gradually. Good.
Yep.
Now, people has that's an evolution theory called Darwinian evolution, and people has take it as it was for many, many years until the 1990s. Now they have this big discovery in southern China, and they found that they look at the fossil record, and they found that there's a period, very short period, all of a sudden new species happened. So before that, there's no, they have that, something new species happened. It's very, very relatively short period of time, I mean, in terms of the evolution. So that actually put a big hole on the Darwinian evolution. So they have to change it. And so basically Darwinian evolution itself is proven wrong, but still a lot of people believe in evolution. But we just don't know if it's right or wrong. So that's the nature when we study the something other than math. And that's also why I like math very much, because in math, we are very clear. And it has to do also just things we study. We study numbers, right? There are just that many numbers. So we can experiment with it, but not in terms of other sciences. There's always something new we don't know yet. And for example, in physics, do you know what that means? The word atom?
It's a very small thing that makes up a lot of other.
Well, the original meaning atom is the smallest element. There's nothing smaller than that. So for a while, that's what scientists believe. That's the smallest element. But then, of course, they can split atoms. They find something actually smaller element inside the atom. So that just show that that's the nature of all the applied sciences. Good?
Yep.
So when we learn algebra or any branch of math, that's the most important thing to learn, is to learn how to do inductive reasoning. Good?
Mhm.
Now, remember what we said before, we have those 10 rules, right? So A plus B is equal to B plus A. Remember that?
Right.
A times B equals B times A. That's why we have those basic rules. So in the inductive reasoning, we have axioms. Axioms is something we all agreed on are true. Then on top of that, we can build theorems. Theorems are to be proven. And once we've proven we know true, then on top of that, so we can build on top of that. Good.
Yep.
But the axioms, the basic truths, basic principles are not that many. So we know that we have what we have. We have, first of all, we got A plus B equals to B plus A. Then we have A times B equals B times A. Good.
Yep.
That's the commutative. Then we have A plus B plus C is equal to A plus B plus C. Now you can see that our rule are different from order operation. Order operation is the rule in elementary school math, but once we got algebra, the rule is a little bit, it's going to be different. Then we have when we multiplies, doesn't matter which two multiplies. In order operation, they said that you go from left to right, but not in algebra. So you got A times B and C. Then we have what? A plus 0 is A. Then A times 1 is A. That's identity. Then we have A plus negative A is 0. And then we say A times 1 over A is 1. Good?
Yep.
So we got
Got it.
A. Then we have the associate property. Sorry, is actually A, B plus C. So we go times that is A times B plus A times C. Then we have A plus B times C, then A times C plus B times C. So that's all we have, 10 rules. Good. That's our foundation. Okay.
Mhm.
Now, based on that, we can build something up. Remember, we do you still remember integers?
Uh-huh.
Okay, now let's kind of use that rule to dealing with integers. First of all, we know this. 4 plus negative 4 is 0, right?
Mhm.
Negative 7 plus 7 is 0. So that's this rule, A plus negative A equal to 0, reverse property. Good?
Yep.
So now we can use that rule to dealing with integer when you add in different integers. Like for example, negative 13 plus 8. How we do that based on the rule. So we're going to do that. We can break this into negative 8 and negative 5, right? Good.
Okay.
Negative 5 plus negative 8 is negative 13. Are we good on that?
Yes.
Yeah. So Jade, are you okay with that?
Yeah.
So Asiya, are you there?
Yeah.
Okay. Are you good with this?
Yeah.
Negative 13 is negative 5 plus negative 8. And now we can see 8 plus negative 8 is what?
0.
0. So we got negative 5 plus 0. Now, what is negative 5 plus 0?
That's just
A plus 0 is A, right?
Mhm.
Yeah.
So it'll be negative 5. Good.
Yeah.
So now we can just use that to do other integers. Actually, integers is really part of the algebra. Just like now they actually teach that a little bit early before algebra. So now we can see, for example, another thing is say 10 plus negative 8. Now the same thing, 10 we can break down to 2 plus 8, right?
Mhm.
Yeah.
Now, then 8 plus negative 8 is just 0. So with 2 plus 0 is just 2. So that is just 2. Good.
okay.
So we can use that. And so everything we did is based on the rule. As long as the things we did based on the rules, we're good. Good.
Okay.
Yeah.
Yeah.
But-
So we know how to use these two rules, A plus negative A equal to 0. And we know a plus 0 is 0. That's very good. So we're going to actually do some exercise about distributed property. Now, distributed property is a, let's say 4, 7 plus 3. Now, in the order operation, we just add 3 plus 7 as 10. 4 times 10 is 40, right?
Yes.
And in algebra, we can also distribute it. 4 times 7 is 28, plus 4 times 3 is 12, and that's give us 40. Good.
Okay.
Got it.
And we also do like do another one. 5, say 10 plus 3, and we can do 5 times 10 is 50, right?
Yep.
Then plus 5 times 3 is 15, so that we got 65. Good.
Yeah.
Okay.
So that's called distributed property. Okay.
All right.
So knowing that so far, now we can look into the linear equations, because we are going to use the rules to solve linear equations. Now, linear equations, for example, something look like this: 3x plus 1 equal to, say, 7. Good.
Yeah.
Now, this is called unknown. We just don't know its value. We know it's fixed. Okay. This technically is not variable. Okay. Variables can take different values, but this is fixed. We just don't know what's the value. We are going to find out. And this is the problem we are given, is that this 3 times that number plus 1 is 7. So that's given. So we assume this is true. Now, if we assume this is true, then what are the consequences? So that's what we call by logic, right? Step by step. So now we're going to apply with the rules. The first thing we're going to do, we can add -1 on both sides. Good.
Okay.
The reason we can do that is we have this property. Actually, this is right after the 10 rules or 10 properties. Is if A is equal to B, then A plus C will be equal to B plus C. Good.
Okay.
Yeah.
Okay, so this is what we see, right? We can agree on that, right?
Yep.
Okay, so therefore, that's why we can do that. We use this property. And then when we add them, what happens? We know 1 plus -1 is 0, right?
Right.
Mhm.
So we got 3x plus 0. And the other side just dealing with numbers. So that's elementary school stuff. 7 plus -1 is 6. Good.
Yep.
And that we use this rule, a plus -a equal to 0. And then we're going to use a plus 0 is a. So that means that's 3x equal to 6. Good.
Got it.
And then we're going to use this rule. If a is equal to b, then if you multiply exactly the same thing on both sides, the equation is still true, right?
Right.
So like say 3 equal to 3, if you times 4 on both sides, that's still the same value, right?
Yeah.
Make sense?
Yeah. Definitely.
Okay, so those are our basic, we call it first principles. We know this is true. We know this is true. And so because of that, we can apply that here. And so far we are playing by our rules. As long as we play by rules, the answer we got is will be correct. So now we're going to multiply something on both sides. The thing we're going to multiply is actually the reciprocal of 3. And we know we can do that is by this rule. So, but the reason we multiply by the reciprocal 3 is that we want to cancel that. So we know a number times the reciprocal is 1, right?
Mhm.
So we got 1 times x equal to, now 6 times 1/3 is 2. Good.
Yep.
And but
Yeah.
and then we know a number times 1 is a number itself, right?
Yep.
So therefore that gives us conclusion x is 2. Good.
Yeah.
Okay.
So that's how we solve it. the linear equation. So basically we came with this. We assume this is true because this is a given. We actually really don't know whether or not it is indeed true, but that's we assume that's something we are given. So we assume it's true, but if this is true, then we can do this, right?
Mhm.
And because we can do that, then we can also do this. Good.
Yep.
And then we can do this, and then we can do this, then we can do this. So when you do algebra, when you're trying to prove something, it's always if then kind of sentence. If this is true, then this is true. If this is true, then this is true. So basically, if this is true, we'll have consequence. What's the consequence here is we know x has to be 2. Good.
Got it.
And this is very powerful because not only we say x, the solution is 2, and we can only say with certainty that this x equal 2 is the only solution. Good.
Yep.
Because we follow the rules. Once we follow the rules, that's the only solution we got is x equal to 2. Good.
Got it.
Very good. So this basically is how we solve linear equations. And next time we're doing more. But today, what's important is to understand what the most important thing that when we are learning algebra is to learn inductive reasoning. Okay.
Okay.
Got it.
And that is what people call, at least people used to say that that's something is rational. Good.
Okay.
Like we are told that we need to think rationally. We want to be rational thinkers. It's because this. It's because the inductive reasoning. Because the logic we follow. Good.
Okay.
Yeah. So
Yeah.
that can help us to make rational decisions. So sometimes we might not feel this is the right answer, but the logic shows us this is indeed the answer. And that happens in science all the time, is that they came up with a conclusion which is counterintuitive, but they know their logic is sound. So therefore, the conclusion itself is not wrong. It's just our intuition is wrong. Good?
Yeah.
Okay, all right. So I'll see you next week.
Okay.
All right,
Yep.
bye.
Bye.
Bye.